Solutions that have been developed over the last many decades are inherently ill-suited for the machine learning workload. All of these computers are based on a 80-plus-year-old architecture. Adopting a new technology like this doesn't mean you have to change everything you're doing. Almost 3 years in R&D. When one CMOS transistor, something that would take hundreds or thousands of transistors.
How little power this actually needs to do its job, because that's the game changer.
Make deductions of new data that you've never seen before.
Hello IPXers. We've now completely drawn to the end of our exploration of Electronica 2024. We've spent all week finding innovative, incremental improvements, because that's what we do. We look for disruptive technology for you. We wander around the exhibitions and we find stuff that's going to help you with your next project, be it IoT, wireless, whatever, automotive, whatever you're looking into. We're finishing off our coverage of Electronica with Niraj from a company called Blumind. I'm not quite sure where this conversation is going to go, but I know you're going to find it interesting, because we're going to be talking about the world of AI, machine learning, and why his technology, which is analog machine learning, which he's going to explain the difference between digital machine learning. And we're going to have a chat about the future of AI. We're going to have a chat about low power applications and why actually the choice of how low power he can go compared to existing, we're not going to call them legacy because it's not legacy technology, none of that stuff is legacy technology, but why you would go in that direction. So I'm going to start with my two Ronnie's gig joke, which you've heard me go on about before, which is if you met a farmer in a field and you said, I want to find a village somewhere, and he turns around and says, I wouldn't start here. That's where we're going to start that conversation. So,
yeah.
More than happy for you to introduce the company, and then let's have a discussion about the world of AI, what machine learning actually means, why analog is the route to go with machine learning, and why you see the future of that being in low-power wearable devices. Over to you.
Awesome. Well, Guy, great to be here. Looking forward to our conversation. Blumind is what's called a fabless semiconductor company. We're a startup innovating in this machine learning space. We're doing some really important work because we feel very passionately that today's solutions that have been developed over the last many decades are inherently ill-suited for the machine learning workload. Okay. And I'll tell you why. And your little anecdote there was really apt, because if we were starting with no computers today, and all we had is neural networks and the algorithms that run these neural networks, the computers we would build would look very different than the computers we have in the world today. CPUs and GPUs primarily.
Yeah. So you're talking about the actual architecture at that point.
Yes, the actual chip architecture, the hardware that actually runs these algorithms would look very different.
Yep.
The reason behind this is all modern day computers, as you said, it's not legacy, right? These are all very much in the field today, right? These are all being used.
This is really, really up-to-date stuff.
This is all being used in our phones, in our servers, in our cars. You might be surprised to hear that all of these computers are based on a 80-plus-year-old architecture, the von Neumann computer architecture, which served us really well for many decades, but was really designed for human-written sequential code execution. And over the decades, my industry, which is a very innovative industry, the semiconductor industry, has improved that architecture and made it more efficient, more productive, consume less power. But we're hitting up against a wall with this new workload of AI, which is inherently different. Neural networks are nothing like sequential code.
Yeah.
Okay. Massively parallel, trained with boatloads of data, and not deterministic in the way human-written sequential code is. So what we at Blumind saw this coming, and my co-founder John Gosson, who's the inventor of this architecture, saw this coming in his previous job, and decided to do something about it, and really developed our architecture, which is brain-inspired, but because the brain has evolved over millennia to be really efficient at exactly this type of workload. Our brains can very quickly learn and then infer with data that we haven't seen before, very, very quickly, consuming extremely little energy. Right? So this is what we've tried to mimic in our architecture and have done a phenomenal job doing it. So I'll pause there, see if you have any comments on everything I've said so far, then I'll continue.
He's expecting me to ask an intelligent question. So, I understand this concept. So conceptually what we're talking about, because what I actually want to talk about and the question I actually want to ask, so yeah, you stopped at a good place. This whole concept of AI and machine learning, okay, which I've been questioning for quite a long while. And that journey started actually at CES at the beginning of this year, where everybody all of a sudden had AI. We're AI. Right. Machine learning, okay? Now that's a very important statement. Right. When you delve underneath the bonnet and you actually ask about, so what exactly is the machine learning? The actual answer that comes back is actually we're doing amazingly fast processing. So the direction I'd like to go in is to try and understand from you, as these developers of a completely new way or new architecture of looking at a problem. In other words, you wouldn't have started here. I'd like to understand, or I'd like to challenge you actually, and ask you, is the machine actually because my idea of learning is I get a set of data and I make a separate decision based on that data, or I get a set of data and I adapt. Because I think that people use the word learning and adapt, and they're too quick to use the word learning because it makes them sound dynamic and really up to date, and the machine is learning. So instead of this becoming an incredibly long question, I just want you to ask the question: is what's the difference between learning and adapting? There you go, I got there.
It's a good question, and quite frankly, even I get caught up in the semantics and terminologies of these, right? Today where we are, right, Guy, is we have these great neural networks that are basically empty frameworks, if you will, an empty brain, that you have to train with a bunch of data. That data is not just any random data, it's got to be curated, labeled, and actually has a huge impact on the quality of that machine that you're training, right? So the data actually, to a very large extent, dictates the efficiency of your AI. Okay, so you have to do that.
Which is power.
Which is a lot of power, which is a lot of work, by the way, right? Like, people may think that these neural networks come out of the box fully trained and ready to go. That's not the case. You have to very carefully train and retrain and do many iterations of this to get the kind of performance that you want to get for your application. And then you can take that the train network after this machine learning and put it on a device to run inferencing. Inferencing is where you see new data that you haven't seen during training. Right. But because of what you've learned during your training phase, you're now able to make deductions of new data that you've never seen before. Okay. And that's kind of how machine learning works today.
And we're talking about that at the edge.
We're talking about that at the edge.
Yeah. So that's important.
Yes.
It's really important to make that.
It is. Inferencing can happen in the data center as well, but let's talk about devices for a second, right?
Yep.
So if I train a neural network to detect the image of a dog, then I throw tons of data at it and say, these are dogs, these are not dogs, and train the features in the neural network to make that recognition. I put that now I do that once, I put that on 1 million cameras out there in people's homes, and now go into inferencing mode where these cameras now have to detect when a dog appears in front of the camera, right? So that's kind of how it works.
Yep.
Now, that's great, and that's where a lot of machine learning is today. What you kind of touched on is, okay, wouldn't it be nice if I can actually now continue to adapt the neural network to my individual needs at the edge? So for my particular camera and for my particular dog, my pet, that maybe the neural network struggles to recognize, I want it to recognize that as a dog. And I can incrementally train this neural network at the edge to do that for me. So I can adapt that trained network
Yes.
to my specific needs.
So in that case, the learning is nuance.
Yes. Yes.
That's the
Yes.
learning. That's
Yes.
that's what you're describing.
Sure.
So that's when I get confused and I ask the question: is that learning or is that adapting?
Adaption.
Yeah.
Yeah,
I'm just asking.
tomato,
because-
tomato, right?
Yeah.
I think so. It's many people call it incremental learning. You may refer to it as adapting to a particular
Yep.
use case.
Yep.
I think both are fine. What's important to note, though, is
I think why it's important is because if you're trying to do an application, if you're listening to this video,
Right.
you're being asked questions,
Right.
and you've got to try and solve the problem.
right.
And that's why it's important to understand those things. It's important to have
Sure.
this discussion
Yeah.
over and over again,
Yeah.
so that I'm a design engineer
Yeah.
at a wearable, which we're going to start talking about wearables in a minute.
Yeah.
My job is to make my wearable take in data from a sensor,
Yep.
learn or adapt, whichever it is. But am
Yeah.
I being asked to learn, or
Right.
am I asking to adapt?
Right.
Big question. And then I've then got to do it at the lowest power possible. So I've
Right.
got certain sequential decision make. It's a decision
Yes.
tree that's trying to get me to the right point, which is why I think it's important that the industry doesn't just throw out words like machine learning,
Right.
because it's not necessarily what you need AI, but it's the level at which you need AI and
Right.
what you're asking the chip to actually do,
Right.
which is when we then come to architecture.
Right.
Is it digital or is it analog? You then get to
Right.
another decision tree to go, should I go the digital route or should I go the analog route?
Right.
So-
right. So yeah, let's go down that.
Let's go down that
arc,
route. Yeah.
Right.
Yeah.
But I just want to close on one point before
Please
we go
do.
there. As we just discussed, machine learning implies having these curated, rich data sets to train your neural network. That is actually very different than human intelligence, right? I can show a child a picture of a woolly mammoth, one or two pictures, right? They don't exist anymore. I believe they're trying to resurrect them, but that's another topic. But I can show one or two pictures of these, and now I can show that child a video with a woolly mammoth in there, and the child will point it out, right?
Yep.
Okay, that's pretty phenomenal.
Yep.
I used hardly any energy. I used hardly any data.
Yeah.
How is the human brain able to make those connections so quickly? A convolutional neural network would not be able to do that, right?
Right.
If I had two images of a woolly mammoth, it would fail miserably at identifying
Where's the dog?
subsequent pictures. Exactly. So, there's a lot of super interesting work in the data science and algorithm
Yes.
side in the machine learning world, which is going to be super critical as well. Now, that's not our focus, right?
Yeah.
All of those innovations will need to run on chips, and we are focused on making the chips super intelligent. So coming down to the analog and digital, digital chips are, like I said earlier, designed for human-written sequential code largely. They're using the transistor device that's been around for many decades and served us so well as a binary switch, right? It's a
Yep.
binary
Yep.
switch, and we're building these big logic circuits off this humble little binary switch.
Yep.
And it's great because it's simple, it's scalable, it's easy to understand, and we've developed this amazing infrastructure around this that now powers everything we do.
Yep.
Right? So that's wonderful. However, for a workload like machine learning, it is incredibly thermodynamically inefficient to use a switch as your primitive to build out computational
Yep.
elements for these big neural networks, which
Yep.
are neural network processing is not really even a compute problem. It's a signal processing problem. Our brains are not computers with memory, compute, instruction set, compiled from software that runs and runs these executions. Our brains are biochemical signal processors.
Yep.
And that's what
They
we're
are
trying
analog.
to... They are analog.
They are analog.
Absolutely. And they're processing analog inputs
Yep.
from our eyes, from our skin, from our ears. So what we've done is we've said, okay, let's look at this problem differently. Let's look at it from a signal processing perspective. But we're not research folks only. We want to build chips that actually change people's lives and solve problems, right? So the semiconductor process technologies that exist today can build chips in the billions and do that very cost effectively, very reliably. So we want to use that same engine to develop our products. And so what we've done is we've developed this architecture using standard CMOS transistors. We're using the same transistors the digital guys use, except we're using them very differently.
Right.
We're using them as sub-threshold, high-precision, multi-level devices, not just a switch. We can do 8-bit processing in that single transistor. So we can do a weight storage, multiplication, all in one CMOS transistor, something that would take hundreds or thousands of transistors plus memory in the digital world.
So to get ready for this discussion, and I rarely prepare for these discussions, but I thought I'd better prepare for this one. I asked a PhD scientist why you'd use analog for neural networks versus digital. And she said, think about water running freely and not being gated. In the digital world, we stop the electrons, we send them in a different direction, which is essentially what software is doing. We stop it, we then ask it to go in a different direction, therefore that's how a digital system works. If you do it in analog, you are setting the water free to just run free, and that's why it uses so much less power.
I like that. I will up your analogy.
Please
one
do.
more.
Please do, because I can't.
An analogy from my co-founder John. He likes to say this. He says, okay, it's like if you pour a pint of beer in a glass, right? The digital way, and you ask somebody you ask a digital engineer how much beer is in this glass. The digital engineer would go in and say, okay, that's a cylinder, the radius of the cylinder is this, and they have an equation for volume, and here's how high it goes, and come up with that math, right? The analog engineer will look at the markings on the side of the glass and go, yeah, that's a pint, right? So this,
and it's the same thing, but it's just a completely different way of looking at it.
It's a different way of looking at it, right? So you're taking advantage of the inherent device physics of the transistor to actually do these storage and computation steps that are needed for the machine learning.
So we've had a philosophical fireside chat, if you like, at the end of Electronica, which I think is really, really important, because this whole world is right on the edge of everything that we are doing. Pun not intended. Right on the edge. So just to finish, let's have a pitch about this. This is your chip. This is doing a job. And before we got talking, you explained, which we're now going to re-go over, the beauty of this in a wearable. Okay, because what they need is real science. They need to be able to listen to this and go, okay, this might be me. That's the whole point of our content. The whole point of our content is to offer alternatives to what already exists, understand why that might be me, and then go and evaluate it. So, last couple of minutes on this chat, explain where this, we decided this was really cool for wearables, taking in sensor data, but just put in context how little power this actually needs to do its job, because that's the game changer today.
Exactly.
Today.
So first thing, I want to communicate to your audience that adopting a new technology like this doesn't mean you have to change everything you're doing, throw that out the window and start using this.
That's my fault.
No, it's not their fault. It's just important to note that. So Roger, John, and I, leaders in this company, we've spent a lot of time here. We want to spend a lot of energy to lower the bar of adoption. Right? We have to make this easy for people to use.
You've made it low risk.
We made it low risk. So the AI frameworks, the training environments, workflows that the data scientists and algorithm folks are using today do not change with our solution. You use the same stuff.
Right.
The only thing that changes is you use our silicon, our chip, to download your trained neural network on, and off you go. You just sip very little energy. Now, how little energy. That's very crucial as well, right? A lot of people talk about low power, ultra low power, mega low power. Okay, what does it all mean? Our chips are designed to do meaningful machine learning workloads consuming single-digit microwatts of power. Okay, what that means is if you were to do inferencing on one of these chips using a significant recurrent neural network off a coin cell battery, that would run for decades,
Yep.
right, continuously.
Basically forever.
Basically forever. So this is the capability this kind of technology will unlock. And there are a slew of new applications emerging where this is rather important. If you want to run always-on AI in a wearable device, let's say provide an audio interface for a wearable that needs to run many months on a tiny little battery, but you want that interface to be always on so I don't have to lift my wrist or
Yep.
press a button or something like that,
Yep.
well, then this will do that without impacting battery life. If you're building a medical implant that needs to run for the lifetime of the patient, but
Yep.
continuously monitor medical parameters, well, this will do that off an energy harvested medical implant, right? So those are the applications that we're targeting initially in our first phase of rollout of this product to solve real pain points with real applications. In the future, we plan to scale this up significantly to do much bigger workloads. This technology can actually scale to
Yep.
do significantly larger workloads and even do SLM and compressed LLM type of workloads down the road. So,
Yeah.
so we have a rich roadmap to do that as well.
So I think one of the most interesting things about this industry, and this has stayed true for all the time that I've been in the industry, is if you can put any breakthrough technology in the hands of a design engineer wherever they are,
Yep.
they will work it out. They
Yep.
will. Just let me see whether that's me. So
Yep.
so I think the last question, because I think you've articulated, I think we've had a very good conversation to understand the difference between, first of all, just to understand the world of AI, to understand the world between whether we're adapting or whether we're learning. That was the structure of which we went through the conversation. Then we talked about the difference between digital AI and analog AI, and then we finished with, well, actually, I'm sure there's many beauties to analog AI, but right now, the difference in the power that you're going to use is just off the scale.
Key.
It's just off the scale.
Absolutely.
So, if we're going to put this technology into their hands, what kind of evaluation environment are they able to?
Good point.
When they've watched this, they've followed the conversation, they've followed you, they've understood what you've said, they follow the pattern of what you've said, and they've gone, right, that might be me. How do they now evaluate what you've got?
So we're just coming out of almost 3 years in R&D with this technology, moving towards commercialization. This is our first product prototype chip that you see here. We are developing a very rich evaluation kit and platform that will be made available to lead customers and the broader developer community later next year.
Right.
We plan to have this virtualized like in a cloud environment that will make it very easily accessible to anybody anywhere in the world to log in, try out the capability, see if it meets their needs. And we'd love to engage with customers and people looking for these types of solutions.
Okay, excellent. So it's coming.
It is coming.
Can't do it today, but it is coming.
That's right, Gary.
Okay.
Yep.
Okay. Right. The beauty of this video stuff is it's now as an absolute record as we keep going on our journey with content, is that it's now recorded. This conversation actually took place, and as a reference, we had a discussion about analog AI. We had a discussion about the difference between analog AI. He's put his stake in the ground. He's explained why we've started in the wrong place. He's put his stake in the ground to say that's the reason why. And then he's explained that actually, not only is it a philosophical debate, it's an actual real debate, because it's all about, right now, it's all about that very clever, whether you call it learning or whether you call it adapting, it actually doesn't matter. That's an esoteric decision to whether you call it that, but actually it's all about the power. And this may actually be one of those discussions where you look back in 3 years' time and go, well, it was obvious, wasn't it?